Hello everyone. In this lecture we are going to start with another very important and easy topic, that is pumping lemma for regular languages. And in next lecture we will be covering pumping lemma for context-free languages. And to understand this for context-free language, you need to understand it for regular languages first. And in exam you may have theoretical question or the logical question based on this topic, like describe pumping lemma and its applications, or solve this question and prove it with pumping lemma, like this. But you can attempt any type of question with very ease, because we have a couple of rules here that we need to apply to solve each and every question. So let's start the lecture with a brief introduction of regular languages, and then we will be covering the rules of pumping lemma, and we'll also solve a question to prove and to implement all those rules. Okay, so here let's have an introduction of regular languages. So regular languages are the languages that can be recognized by DFA or NFA. Okay, so all languages are regular if they are recognized by DFA and NFA. But if we have any language like this, language a raised to power n, b raised to power n, and n greater than equal to 1, so we cannot construct DFA or even NFA for this particular language. So we can say that this language is not regular, as we cannot construct any DFA NFA for this language. So this language is not regular, right? And or we can conclude that type 3 or regular language is subset of type 2 language, and it is subset of further type 1 language, and further it is subset of type 0 language. So except type 3, no other language can be recognized by DFA and NFA, and these are not the regular languages. Okay, so pumping lemma is a proof for these languages. To prove that these languages are not regular, we will be using pumping lemma rules. Okay, so here the pumping lemma describes an essential property for all regular languages, and those property must be possessed by any regular language. If the condition fails, then we can conclude that the language is not regular. So we will be proving this by taking a long string in the regular language. So we will be taking a sample string from the given language, and for that particular string we must find a specific section that can be pumped, and the repeated string or the new string must lies within the same language. If this condition fails, then we can say that the language is not regular, and we will be having specific rules to prove this condition. Okay, so this condition will be more clear to you once we will be starting with the examples. So we can say that the pumping lemma is basically a negativity test and used to prove a language as not regular or non-regular language. So here suppose we have a particular string, and this string will be divided into three specific sections as x, y and z, and we say that y is a section that need to be pumped. And why we need to pump something? By pumped we means that we are iterating certain section of the or specific part of the string. So or we are having a looping in the DFA to repeat a particular part of the string. So this term is known as pumping. So here if we are having one DFA like this, okay, so with three states as 1, 2 and 3, here the third state is a final state, and we are saying that we are having regular expression for this, as this means a plus positive closure of a followed by a single b. So the minimum string to be accepted here is a and b, right? So for this minimum string we need nothing to be pumped, means a, b as minimum string, length is 2, okay, and this string can be directly accepted without any loop. So this is the expression is proved for this particular minimum string. We need nothing to be looped or nothing to be iterated for this acceptance. But if we have any string greater than equal to, with length greater than equal to 3, means number of states, n is taken as number of states here, and any string with length greater than equal to 3, okay, or number of states in a DFA will surely have something to be iterated or something to be put into the loop for acceptance. So if we have any other criteria string here, suppose we are taking W as a b, okay, then after length 3, okay, we need something to be iterated. So here we must have a loop to iterate further a's for acceptance. So here we are having this y section, okay, or if we are taking the length as 3 only, so if the length is 3 only as this, so here this is x, this is y, and this is z, and we are iterating a, or the y section is iterated for acceptance. So y can be iterated any number of time. If we are having I as 1, then the string is a b, and the string is accepted as it belongs to the language. But if I is 2, the y part is iterated 2 times and the string will be this triple a and b, and the string still belong to the language. So as the definition was saying, we need some part to be iterated any number of time and the string must belong to the language, and if this condition fails, then the language is not regular. So here we can iterate a any number of time, means if we iterate a 10 times, still the language string belong to the language, okay. So the string is still belonging to the language, so we can say that the language is regular. So let's check the rules for this pumping lemma by an example. Here we are having another DFA for string starting with 1 and ending with 0, and we are having any combination of zeros and 1 for acceptance before the last symbol and after the first symbol. So here the minimum string is 10, but to prove the lemma we need the string greater than equal to number of states. Length of string must be greater than equal to number of states to prove the lemma or to put something into iteration. So here let's take minimum string as this, okay. So here the y part is 0, so x part is this, z part is this, and the y part is this. If we iterate y part any number of time, the string will also belong to the language, so we can say that the language is regular. So let's check the rules of the pumping lemma. So for any regular language L, there exists an integer n such that, so n we are taking as number of states. So here w belong to the language for any string w, and the length of w is greater than equal to n, then there exist certain parts, means we can divide the w into 3 parts as x, y, z, and these 3 conditions must be satisfied as length of x and y must be less than equal to n, and as y is the iterated part, and if length of the string is greater than number of states or n, then the iterative part must be greater than equal to 1, means the length of iterative part must be greater than equal to 1, means we need something to be iterated for acceptance, otherwise the string cannot be accepted or the string cannot be fulfilled with number of transactions. So here the last condition that we need to check is for all i's, okay. So means we can iterate y any number of times and the string still belong to the language, then the language is regular, otherwise the language is not regular. So here we will be taking a sample string as w, and for all i's, suppose we have I as 1, then the string is this. So I is 1, y is iterated 1 time. If I is 2, then the y is iterated 2 times, and if I is 3, here the y is iterated 3 times. So I is y or iterative part is iterated any number of time, the string must belong to the language for any number of iteration. If the condition is satisfied, the language is regular, otherwise the language is not regular. Now let's prove the pumping lemma for a given context-free language. So we need to prove that this given context-free language is not a regular language, okay, with the help of pumping lemma rules. So here, as the minimum required string is of length 2, as we need m must be greater than equal to 1. So here the minimum string is AB and the length of minimum string is 2. So we need to take a sample string that is greater than length of the sample string must be greater than 2. Then we have to divide the string into 3 sections, x, y and z, and then we have to check the pumping lemma rules. Now the sample string must be, length of the sample string must be greater than equal to 3, as the minimum required string is 2 here. So we can say that n is 3 here. So the sample string's length must be greater than equal to 3. Now as we cannot have a length 3 string for this particular language, so we will be taking the sample string as AA, and the length of this string is 4. Okay, so the sample string here is AA, and we will be dividing the string into 3 sections as x, y and z, and every section is having the input symbol. So x is A, y is AB and z is B. Now as x and z part can be null, remember this, x and z part can be null, but the iterative part cannot be null. So we need something to iterate if the length of the string is sufficient enough for acceptance. Okay, so now as the string is AA, and this is x, this is y and this is z, you may take any other partition. Now we will be proving that this string is, or this language is not regular with this sample string and with this partition of x, y and z. Now the first rule was length of x and y must be less than equal to n, and as the minimum required string is 2 and n we have taken as 3. So n is 3. So length of x and y part must be less than equal to 3. So here the length of x and y part is, as we can see, length of xy part is 3 and that is less than equal to 3. So first condition is satisfied. Now check for the second condition. If any of the condition fails, the language is not regular. So now we are checking for the second condition. Now the y section is, the length of y must be greater than equal to 1. So here the length of y section is 2, that is greater than equal to 1. So the condition is also satisfied. Now we have to check for the third condition, means any if we iterate y part any number of time, the resulting string must belong to the language. And if we succeed to find any I, with any iteration of I, and the string doesn't belong to the language, then the language is not regular. So let's check for the I iteration as by taking the sample string as this. So we will be checking for the iteration of I. For 1, I equals to 2. So what will be the string or resulting string after I iteration? If we are iterating y 1 time, if we are iterating y 2 time, and so on. So let's check for the strings here. After the first iteration, as I equal to 1, so the W is x, y raised to power 1 and z. So the resulting string is AA and BB, and the string is in the language. So we can say that this sample string belong to the language after one iteration of y part, but we cannot conclude the language is regular with this particular check. Okay, so we have to check for further i's as well. Now for I equal to 2, with 2 iteration of y part, the string will become A, AB and AB and B. Now this string is no more in the language. So we can say that as this string doesn't belong to the language, so the language is not regular. So this language is not regular as this condition fails at second or two iteration of I. The language is not regular. If we take any other iteration, let's take any other partition, so if we take any other partition and we are taking this section as, we are taking first two symbol as x and the third symbol as y and fourth symbol as z, so x, y and z. So if we take this partition also, even then for I equal to 2 the condition is not satisfied, as after two iteration the string will be this. We have this sample string double A, and now y part is iterated two times, so we are getting 3 b's. Okay, so this is x, this is y and this is z now, and the string doesn't belong to the language, so the language is not regular. So you can check for any type of partition with any type of sample string greater than, sample string with length greater than equal to n, and prove the lemma. Okay, so this is the way how you prove the pumping lemma for a given type 2, type 1 or type 0 language for regular language pumping lemma. And we will be in next lecture we will be checking the conditions to prove a language for context free language pumping lemma, where we will be working with type 2 language and type 1 and type 0 language, because type 2 is context free. So we will be working with the type 1 language to prove the language as not a context free language. So till then, bye and take care.